Hello everybody, this is Navid Babani. Welcome to my channel Power Synergy. Today we are going to talk about the solar cells and how temperature affects those solar cells. Temperature has a significant effect on the performance of solar cells, and this impact can be both positive and negative. The relationship between temperature and solar cell efficiency is complex and involves several factors. One of the main factors is temperature coefficient. Most solar cells experience a decrease in coefficiency as the temperature increases. This is often expressed as the temperature coefficient, which is measured of the percentage decrease in efficiency for every degree Celsius increase in temperature. The temperature coefficient varies among different types of solar cells, so choosing the correct solar cell, that's a proper solar cell, is really important when you want to design your solar power plant, let's say. And there are also other factors I don't want to mention so much about cooling system for some solar, let's say, fields. They have cooling system to increase the efficiency. I will show you the plot and how it differs for different temperatures, the efficiency of our solar panels. And it will be simulated in MATLAB and it will be shown here.
As it is shown here, you can see that we have the short circuit current and open circuit voltage. These two barriers shows the boundaries of our plot. But by multiplying voltage and current, for sure we get the power. But at some point it's not possible to have the maximum voltage and maximum current at the same time. So the junction between the functional voltage and the functional current is set here, that it is our maximum power point that we call MPP. And we will show this plot in our simulation as well. You will see that how temperature affects this curve, the power curve, and according to the temperature, the power can be higher or lower. Let's see what's going on here. But according to the experience and experiments, the higher the temperature we have, the lower the power we can get from the system. Alright, here is the Simulink part you can see on this screen. For the first part, we need to have some irradiation in our solar panel, the radiation that we get from the sun. So let's have it with 1 PS constant. Let's add it here. PS constant, we have it here. Then for the constant, we can consider that as 1000 because we say it with power over square meter. And let's consider that as 1000 let's say watt over the square meter. Okay, after this part, now it's time to add our solar panel. Solar cell, let's say, and connecting our constant to our solar panel. By double clicking to this solar panel, you can see there are some parameters. For irradiance we have 1000, as you can see here. There are also some other factors, that open circuit voltage that I explained in the beginning of this session. Short circuit current, it is 7.34, and we can adjust it and we can change it to any parameter that we want. All the other configurations, just like panel configuration or temperature dependence and cell characteristic, the other parts will be explained separately in another video for you. In this part, what is important for us is the device simulation temperature, because we want to show you how temperature affects the performance of these solar cells, how it affects the power and voltage, let's say power of these solar panels and solar cells. You can also change to the other parameter with 8 parameters or 5 parameters. Let's keep it this way. And for RS resistance also, that's a tiny amount for the RS. And then we need to have the grounding here. We're going to add electrical reference in this part and connect it to the cathode part of our solar cell. To the positive part of our circuit, we add current sensor to sense the output of the current to our system. And from the output of this, let's say, current sensor, we can connect it to a scope. I can connect it. Hold on a second. To be able to connect these two parts, we need PS Simulink converter. Simulink converter, as you can see it here. Then there we have. From the first part of our scope, we can get the current for sure. And then we have our controlled voltage source. Controlled voltage source, the second one here, not this one. While choosing the controlled voltage source, be careful to choose it from the foundation library that we have our, let's say, blue line libraries to be able to connect the components to each other. And then connect the negative part to the negative part of our panel. There we go. So we have controlled voltage source here. We have the current sensor and the irradiation that we have got it from the solar, this is from the sun. Don't forget to add solver configuration to our below system and add it here. So let's rotate it to, so you can find rotate. The block. Okay, cool. Let's also flick this block. Right, good, nice. To be able to increase the voltage, we need to have a ramp here. And let's flip it again. Format, flip block. And here we are. As you can see, we can connect them to each other. So what we're gonna do, we should again have PS Simulink converter. Yeah, there it is. Here's the converter, rotate it again. And then connect it to the controlled voltage source. We can call this one as kind of test voltage, let's say. Test voltage or load voltage that we get it from the system. As I explained previously, solar panels are passive elements, so they adjust their voltage according to the load that they get from the system. At the end, we need to we have our current plot here. Let's add a max here. Max. Increase it to 3 ports. Number of inputs, 3. Then we can designate the first one for the current, second one for the voltage that we get from here, and the one in the middle can be the product of the current and voltage, which means power. So what we need to do, we need to add the product here. Now let's zoom in. And it can be the multiply of current and voltage that we get in our second input of our oscilloscope. There we go, everything's going well, and let's check the system. Everything must be fine. There are some adjustments that remain. Now it's time to run the system. You can see the stop time is to adjust to 0.073, and you can add the test voltage to 500/40. I'll tell you all these adjustments. And the open circuit voltage is set to 0.9. Now let's run it and see what the result is. Go to our scope. You can see the current decreases after some point, after the voltage increases, and the blue one is our power plot, the yellow one is our current plot, and the red one is the voltage plot, as it was explained previously in the beginning of this session. To be able to show the effect of temperature in our system, what we're gonna do, we can copy and paste all system, the same one here, with the same radians, with the same constants. But for this one, the radians are the same, but let's change the temperature, for example, to 60 degrees. And let's see what's going on, what the differences are when we add them to that one. We can have the scope to version. Let's make the number of inputs to 2. And OK. Here we go. And the other one here. And let's run the system and see what's going on here. As you can see, here's when the temperature is lower, we have this yellow one, and when the temperature is higher, we have this, let's say, green line for the current. For the power factor, until this time it's fine, and the blue one is for the upper version when the temperature is 25 degrees, and the purple one is for when the temperature is 60 degrees. So as you notice, temperature is so important, and it affects the power and efficiency of our cells, as it is obvious here with the same voltage rate here, and here's in our time domain, but with the same voltage rate, you can see that the power will be higher when the temperature is lower or in its proper area.
To sum up, we saw that with different temperature, we have different power voltage curve. Shift in the maximum power point, MPP, happened. The PV curve is a graphical representation of the solar panel power output at different voltage levels. So the MPP, which represents the maximum power output, tends to shift with the temperature changes, as it was shown in our graph in the MATLAB. Solar panels are typically designed to operate at a specific temperature range, and deviations from this range can lead to suboptimal performance. So choosing the correct temperature is really important choosing the, let's say, correct MPP, the function or the operation point is really important for our system. So the impacts on system performance. Understanding the PV curve under various temperature conditions is crucial for system design and optimization. Engineers consider temperature coefficients and thermal characteristics when designing solar panel systems to ensure that the system operates efficiently across a range of environmental conditions. So those environmental conditions can be temperature, can be lots of other things, the radiation that we get from the sun, and lots of other factors. There are also, how can we overcome this temperature problem? There are some cooling strategies. Some solar power systems incorporate cooling strategies to mitigate the negative effects of high temperature. Active cooling systems such as fans or liquid cooling can help maintain the solar cells at an optimal temperature, improving their overall efficiency and performance. So in summary, we see that the effect of temperature on solar cells is reflected in the changes observed in the power voltage curve. Temperature influences key parameters such as open circuit voltage, short circuit current, field factor, and position of maximum power point, which is MPP. And understanding these relationships is crucial for designing solar systems that can perform optimally in diverse environmental conditions. I hope this video finds you well and you learn about the relationship between the temperature and the solar panels. I will explain the boost converter later on in our next videos to see how we can increase the efficiency of our solar panels by using boost converters. See you later on. Thank you for watching.